Hey there, it's Modern Retro Tech, and today we will look at Rust ecosystem again. This time we will explore a system called Timely Dataflow. It's a streaming processing engine written in Rust. I'm very excited to try it because it is something quite unique. Judging from the documentation, I had a brief look to it before, but I haven't actually used it, so today we'll be learning it together. I plan to stream for about 2 hours today, so if you won't be done, I think I will do a follow-up. Also, by the way, I'm still working on the video about graphs, so that is still coming. I'm just editing it, a bit more patience, and it will appear on my channel. And I plan to keep up doing both longer live coding streams and also some shorter edited videos about specific topics. Also, this is live stream, so if you have questions, feel free to ask them in the chat. I will be checking it out regularly and we'll try to answer your questions. So that being said, let's start. And this is how Timely Dataflow repo looks. You can see that it's quite a popular project. It has about 2K stars on GitHub and 39 contributors, and it seems to be updated regularly, which is quite important because that shows you that the project is actually used. Then it has really nice documentation. So it has a Timely Dataflow book, and of course it's also published on Crates.io, so you can easily depend on it, and it also has a normal Rust documentation. So apart from that, it also has another project called Differential Dataflow that provides a high-level interface for it. And there are a bunch of example apps that are also written using it, so you can try it out. Hey, hi. So you can try it out both as like basis of your system if you want to go really low level, or you can try it out for like more high-level tasks with typical combinators and stuff. So let's set up a new project. How shall we call it? Let's just call it, now Timely may be a bad name, streamer, not how it sounds like, but nope, not that. Yep, okay. So let's maybe move it here because we'll need to see our documentation still. And let's also add it to dependencies. I believe the name is just Timely. Yeah, exactly. One thing that I always try to check about those projects, it's also the versions that they have. So what was the latest versions and how often it is updated? Interesting, it had a peak of usage in December. And here you can see that they have some new versions, so 0.11. Okay. So let's just try to run it. I think it doesn't have too many dependencies here. It's only 24 dependencies. So it's pretty lightweight project. For those who are joining right now, what we're doing today, we're trying Timely Dataflow. It's a streaming processing system written in Rust. So we will try to learn it a bit today. And yeah, it depends on a bunch of things. So proc macros, scene, Serda, Unicode widths, a bunch of its own dependencies. Abomination is apparently a serialization library written specifically for it. Getopts, quote, scene structure, and then some submodules. So, well, very lightweight project, it seems, which is always nice. Let's check out the Git book. So first it's intro, and then it has a bunch of examples. So examples we like, let's do examples. I really wonder if we still need to write the external crate stuff. I'm not so sure. I think we can just comment it out, but first let's try to run it like that. So what does this thing do, judging from the code? It calls timely example. I guess example is like test executor. We execute a single-threaded timely data flow computation. Exactly. Takes a closure on a scope which it executes to initialize and run a timely data flow computation on a single thread. This method is intended for use in examples rather than programs that may need to run across multiple workers. Okay, so it's like to try it out, to try the API itself out. And then we create a range from 0 to 10. We call to stream, converts to a timely stream using this scope thingy, which I have no clue what it means yet. And then we just call inspect, runs a supplied closure on each observed data element, where we just print stuff. Okay. Sounds fancy enough. Let's run it. Okay. One thing that I always try to see is also how much space the binary with this library will take, because it also gives me a bit of a perspective about how easy it will be to distribute it. I would expect it will be, I don't know, 10 megabytes, maybe less. But let's compile it. And of course, it's also interesting to see how fast it will actually run when it is compiled in release mode. So one thing, while it does that I want to do, let's take, whoops. No, we are not learning threading. We are learning timely data flow. It's this streaming processing library in Rust. We are trying it out. Gosh, I'm so dumb. It's third day of weekend, so I will be a bit slow. Sorry about that. Yes. Okay, so now we can reformat it a bit better. Okay, we have finished creating that. And now we can, gosh, target, release, yep, okay. And then we have build. Okay, so streamer, oh wow, it's very small, it's half a megabyte essentially. And we can of course try to run it this time. So here, of course, the whole time is just spent printing to console, but okay. This program gives us a bit of a flavor. Yeah, it gave. This isn't very different. Why would we want to make our life so complicated? The main reason is that we can make our program reactive so that we can run it without knowing ahead of time the data we will use, and it will respond as we produce new data. Okay. Timely data flow means to capture a large number of items, so it is a bit tricky to wrap together one example that shows off all of its features, but let's look at something that shows off some core functionality to give a taste. The following complete program initializes a timely data flow computation in which participants can supply a stream of numbers which are exchanged between the workers based on their value. Workers print to the screen when they see numbers. You can also find this as examples, hello RS, blah, blah, blah. Okay, let's try that now. One thing though, so we can build this stuff. I want to try to remove the external crate stuff because I think it's not needed anymore in Rust 2018. Okay, it was built, let's try that. I was right. So we can remove this stuff. Okay. And what does the code do? Initializes and runs timely data flow. This is useless comment. Let's remove it. Time execute from args. Okay, it accepts some arguments and then it takes worker. This type worker. Okay, it's a closure. Worker index. The index of the worker out of its peers. So I guess it's just like ID, actually, not index. Weird. Let mute input handle new. I guess handle to an input stream used to introduce data to a timely data flow computation. Okay. Create a new input, exchange data, and inspect its output. Worker data flow scope. Oh, data flow. Construct a new data flow. Okay. It takes the scope thing. We saw it before when it was working with the, where it was just like taking a stream of numbers. So that's something similar, I guess. Now, exchange records between workers. The closure supplied should map a reference to record to a U64 whose value determines to which worker's record will be routed. So it's like in Spark it would be shuffle or something like that. Inspect worker. And then the that drives me crazy. I will change it to ID because otherwise it is very confusing. So and then it does probe. Constructs a program probe which indicates which timestamps have elapsed at the operator. Okay, that sounds cryptic. Introduce data and watch. Yay. For round in 0 to 10, if index is 0, input send. Sends our one record into the corresponding timely data flow stream at the current epoch. Okay. Inputs advance to. Advances the current epoch to next. So it has some kind of a thing to track time. This method allows timely data flow to issue progress notifications as it can now determine that this input can no longer produce data at earlier timestamps. Okay. Then it returns true if and only if the frontier is strictly less than time. It sounds more and more interesting, so let's just run it and see what happens. I probably need to supply some kind of arguments for that, by the way. So, blah, blah, blah. Okay. Because it says execute from args, but then honestly I don't. Okay, there's like one worker and it just prints 0 to 10. Not very exciting yet. Okay. We can run this with multiple workers, so there's the fun starts finally. Using the -v of workers flag followed by the number of workers you wanted in the process. Notice that you'll need and blah blah blah. Any arguments before that are treated as cargo command arguments. Sure. So we can do that. Let's do 2. And then hello. So this round thing, it adds plus to it there. And then it calls step. So I guess it updates timestamp or something like that. And here, stop. And this while probe less than put time. Timestamp. Input from exchange inspect. Like I guess this exchange just like sends it to another thread. Okay, if you try with 3. 1, 2, 3, 4, 5, 6, 7, 9. Okay, this is interesting, of course, but can we actually, so if I say HTOP and I will run it with, for example, with 4 workers. Oh, and I will run it till like, I don't know, 100 million. Oh, ID, of course. Okay. And here then. So, if we will try to create a tree, and then will it work? Oh, I forgot it doesn't check to mouse input, and I'm afraid to, let's do it better here, because I may regret it otherwise. So we have tree, and then we have this streamer thing. Does it actually execute in multiple threads? I don't see it. It just says, I think it still executes in one thread. It just has like 4 logical workers or something. Because it is interesting. Okay, whatever. Let's continue. So No, it sounds it spun up two worker threads. Okay, maybe there's something interesting how it spans them up, but I haven't noticed that. Notice that the work index is now varied. There is only clues that different workers exist and process different pieces of data. Worker 0 introduces all of the data. Notice the guard in the code. Without this, each worker would introduce 0 and... Oh, okay, so let's change it and see. Will each of those now? Let's do 2. Compile it and see. Oh yeah, true. So this is interesting. But this way, it always will start from worker 0. And then it is shuffled between the workers. The only guarantee is that records that evaluate to the same integer in the exchange closure go to the same worker. In practice, we currently wrote records based on the remainder of the number when divided by the number of workers. Okay. Finally, let's run with multiple processes. Okay, that's funnier. To do this, yeah, oh my god, of course, each top will show different processes, but not different threads. So I did too much Python. To do this, you use the -n and -p arguments, which tell each process how many total processes to expect and which index this process should identify as the -p parameter. You can also use -h to specify a host file with names and ports of each of the processes involved. Oh, that's pretty cool. So you can kind of do distribution. But if you leave it off, Timely defaults to using localhost. For new joiners, we are learning Timely Dataflow today, checking out the docs, trying out examples, trying to make sense of it. It's a streaming processing engine written in Rust. Sounds quite exciting, so far at least. Now we will try to run the same computations that we ran with one stream. We then ran it with multiple streams, and now we will try to run it with multiple processes. So, I guess then we say we have two processes, and this is the first process. Nothing yet happens. Ooh, this is interesting stuff. Okay, let's make it work like that then, because I want to see both of those. And then we can take this and do this, I guess. Whoa, nice. So now we know that it's really distributed. You can see that both of those executed. And now, of course, let's make it a bit fancier. Let's make it 10 million. I really like how it waits for this thing to appear. Whoa, pretty fascinated stuff, because I really like that it synchronizes it somehow. It seems to be quite minimal in terms of synchronization. Well, and that's what happens when you break it. So it really, what is the error? Let's see. Connection reset by peer. Okay, it's reasonable error. And where does it panic then? It panics in timely communication. 0 copy TCP. So I wonder. Okay. So we can run the same computation from one process, from multiple processes, or in multiple threads. Neat. However, our computation so far is pretty primitive. Okay. When to use Timely Dataflow? Data parallelism, streaming data, expressivity. Timely Dataflow main addition over traditional stream processors is its ability to express higher-level controls constructs like iteration. This moves stream computations from the limitations of straight-line code to the world of algorithms. Okay. And it's also apparently general. Okay. When not to use Timely Dataflow. Oh, that is always a good sign to see something like that in docs, because it says to you that people actually put some thought there. You often see only pros but never cons, and that's always kind of a red flag. Here they say also sometimes you shouldn't use it. Nice. I've collected a few examples here, but the list may grow with input and feedback. Timely Dataflow is a data flow system, and this means that at its core, it likes to move data around. This makes life complicated when you would prefer not to move data and instead move things like pointers and references to data that otherwise stays put. Okay, so like sorting data in a slice is not really a good task for that. Data flow systems are also fundamentally about breaking apart the execution of your program into independently operating parts. However, many programs are correct only because some things happen before or after other things. A classic example is depth first search in a graph. Coming in our other series. Although there is a lot of works to do on small bits of data, it is crucial that the exploration of nodes reachable along a graph edge completes before the exploration of nodes reachable along the next graph edge. Blah, blah, blah. So if you don't know how to transform it to parallel execution, don't try it. Okay, Timely Dataflow is in a bit of weird space between language library and runtime system. This means that it does quite... Oh, I think you cannot see shit now because... let's just... it didn't make things better. It made things kind of worse. Okay. Okay. Timely is in a bit of weird space between language library and runtime system. This means that it doesn't quite have the stability guarantees of a library might have. When you call data sort, you don't think about what if it fails. Nor does it have the surrounding infrastructure of Triad Link, never heard, or Spark style of experience. Part of this burden is simply passed to you, and this may be intolerable depending on your goals for your program. Okay. Core concepts, yay. So I see timestamps and I see progress. So that sounds like something that probably will give us a bit of a clue about what we should expect. Timely Dataflow relies on two fundamental concepts, timestamps and data flow, which together lead to the concept of progress. So data flow is fundamentally about describing a program as independent components, each of which operate in response to the availability of input data. So that's why it was waiting when we started those two processes, because then it was kind of, okay, nobody is introducing data yet. I guess that's how it works. As well as describing the connections between these components. The most important part of data flow programming is the independence of the components. When you write a data flow program, you provide the computer with flexibility in how to execute your program. Rather than insisting on a specific sequence of instructions the computer should follow, the computer can work on each of the components as it sees fit, perhaps even sharing the work with other computers. Okay. Timestamps. While we want to enjoy the benefits of data flow programming, we still need to understand whether and how our computation progresses. In traditional imperative programming, we could reason that because instructions happen in some order, then once we reach a certain point, all work must be done. Instead, we will text data that move throughout our data flow with timestamps, including roughly when they would have happened in a sequential execution. Okay. Doesn't make a whole lot of sense yet, but I guess it will make a bit of more sense later. Timestamps play at least two roles in Timely Dataflow, as allow data flow components to make sense of the otherwise unordered inputs they see. I received the data in this order, but I should behave as it arrived in this order, and they allow the user and others to reason about whether they have seen all of the data with a certain timestamp. Okay. Finally, progress. We don't have to worry about whether we considered all the numbers yet, because the program makes sure not to provide answer. So yeah, we don't know if we processed everything, so if we combine data flow program structure with timestamp data in such a way that as data move along the data flow, their timestamps only increase, we are able to reason about the progress of our computation. More specifically, at any component in the data flow, we can reason about which timestamps we may yet see in the future. Timestamps that are no longer possible are considered past, and components can react to this information as they see fit. Continual information about the progress of a computation is the only basis of coordination in Timely Dataflow and is the lightest touch we could think of. Okay. So, another example. Data flow programming is fundamentally about describing your program as independent components, each of which operate in response to the availability of input data, as well as describing the connections between these components. Okay. So, let's copy this magical code and so we again use timely execute from args. We then take the this stuff. We create a worker. We then look index ID. Okay. Oh god, no! It really calls it index in the library. Oh man, this is annoying. Okay, that's the same as we already saw before. Then we get. I think it's the same exact program. Yeah, it's exactly the same program. Haven't we seen this example already? Okay. I guess it just explains it now. So there are two data flow operators here, exchange and inspect, each of which is asked to do a thing in response to input data. The exchange operator takes each datum and hands it to a downstream worker based on the value it sees. These two workers, one will get all the even numbers and the other one all the odd numbers. That we already saw. The inspect operator takes an action for each datum, in this case printing something to the screen. So exchange essentially just funnels it to like if you have n workers, I guess it funnels one nth of input to specific worker. So importantly, we haven't imposed any constraints on how these operators need to run. We removed the code that caused the input to be delayed until a certain amount of progress had been made. And it shows in the results when we run with more than one worker. Okay. Okay, so that was like the code that before made it ordered. Worker step while. Interesting. So however, this is only a mess if we are concerned about the order. Gets to print hello 4. Okay, this is interesting. Imagine instead of just printing the number to the screen, we want to find out which numbers are prime and print them to the screen. We'll need to test factors up to square root of x. Let's try that. Why not? This is like alternative inspect. Can I also print this? Oh, cannot infer. Oh, okay. Oh, interesting. Okay. So this is like lifetime fun is incoming, I guess, if you use it. Okay, so both of those workers. Okay, I see. Of course, only 2 is the only even number that is prime, so makes sense. So limit all. Let's check time. It's 2 workers. Okay. Let's try that as well. Let's try to make it run longer. To 10,000, they say. Okay, let's try to print that to 10,000 and actually I probably should let's better do other things. So let's remove this thing and let's do cargo build release, because then we can see how fast it will go with actual input, right? Zero 0.4 seconds and 29 kilobytes. How many lines? So 1,000. Well, there is only 1 worker right now, so. And if you try to do the same thing with 2 workers. Oh yeah, so it's 2 times less time. And, oh well, I use the same output, but doesn't matter. It's same size. It's same amount of lines. Now I guess it will show that. Do we even have workers there? Yeah, only for 2, and this was like the last thing that it did. But this is pretty cool because we already got kind of like parallel computation, where we have a binary essentially where we can specify this -w parameter, and depending on how much we say, it will create like multiple workers and run it. If you say 4, well, in this case, it actually increases, I guess, because of additional coordination. But with 2 workers, it worked faster than with 1, so that is good. Yeah, so they also do release. This is also, okay, this is interesting piece. Man, okay. So, this is also a fine time to point out that data flow programming is not religion. There is an important part of our program up above that is imperative. So this is program for printing all those prime numbers in arbitrary number of workers using timely data flow. And this thing is the primality test. which is it imperative? There is no mutation. Actually, it does print length, so it does side effects, so you can say that it's imperative. This is the imperative fragment telling the inspect operator what to do. We could write this as a data flow fragment if you wanted, but it is frustrating to do so and less efficient. The data flow fragment lets us do something important, something that data flow is bad at. The all method above stops as soon as it sees a factor of x. There is a time and a place for data flow programming and for control flow programming. We are going to try and get the best of both. Okay, that sounds cool. So I guess all equals imperative here. Then logical times. We are actually progressing quite nicely so far. We have been looking at it for like 45 minutes right now, and we are already almost done with chapter 2, which is pretty nice. And so far it makes sense, which is even nicer. So when data flow programs move data around arbitrarily, it becomes hard to correlate the produced outputs with the supplied inputs. If we supply a stream of bank transactions as input and the output is a stream of bank balances, how can we know which input transactions are reflected in which output balances? Yep. The standard approach to the problem is to install timestamps on the data. Each record gets a logical timestamp associated with it that indicates when it should be thought to happen. This is not necessarily when in terms of the date time a specific nanoseconds record was emitted. A timestamp could simply be a sequence number identifying a batch of input records. Or, and we will get into the terrifying details later, it could be much more complicated than this. Okay. Timestamps are what allows us to correlate inputs and outputs. When we introduce records with some logical timestamp, unless our data flow computation changes, the timestamps we expect to see corresponding outputs with the same timestamp. Okay. An example. Okay, I really love the concentration of examples here. Remember from the data flow. Just one printing the timestamp because inspect doesn't have access to it. Oh, so there is like another thing, inspect bunch that also shows timestamp. No, gets low level access to data in Timely Dataflow, in particular access to batches of records with the same timestamp. It is intended for diagnosing system level details, but we can also use it to see what timestamps accompanies data. Okay. So I guess let's better return to this thing where we just print I guess let's do this. And let's also make it again smaller number here so that we don't have so much stuff happening at the same time. Okay, nothing has changed yet because we have the same program. It's just two workers printing those numbers. And now we add this inspect batch stuff instead of. Can I actually do both just for the sake of it? Let's try to do both and see what happens. Ooh, so 1, 3, 5, 7, 9. So this is like timestamp, right? Let's do it better like that because I think it makes more sense. Okay. Okay. So we got like all those numbers, and then it prints worker 1 time 1, 1. Worker 0, 1 times 3 is 3 times 5. So each of those gets their own timestamp currently. So there's like no difference between batching and like normal inspect, because it's the same exact stuff, right? Yeah, that's better, I think. The inspect batch predicates blah blah blah. So we saw that. Of course, we can also just switch to this view only. It's exactly the same. The timestamps are the thing for various. Oh, why does it have this root thingy and we don't have it? I guess it was deprecated or something. Well, T is just pointer to U64, reference to U64. So, and XS is a reference to slice of U64s. There is like no difference. Timestamps are things for various that happen to correspond to the data themselves, but had we provided random input data rather than I itself, we would still be able to make sense of the output and put it back in order. Okay. So, we looked at data flow timestamps. Now we will look at progress. Okay. Both data flow and timestamps are valuable in their own right, but when we bring them together, we get something even better. We get the ability to reason about the flow of timestamps through our computation, and we recover the ability to inform each data flow component about how much of its input data it has seen. Yeah, so we had this probe thingy. Let's uncomment it. And let's now if you run this in, so now it's again back in order when we uncomment this line. We'll put the whole program up here, but there are really just two lines that deal with progress tracking. Input advanced 2, okay, and worker step file. Let's talk about each of them. The input structure is how we provide data to a timely data flow computation. It has a timestamp associated with it. Initially, this timestamp is a default value, usually something like 0 for integers. Whatever timestamp input has, it can introduce data with that timestamp or greater. We can advance this timestamp via the advance2 method. So that's how timestamp actually get updated. Oh, okay. I really need to break stuff. So let's try to comment both of those lines out and see what happens. Oh, oh. Whoa. It doesn't even compile. Ah, so it doesn't know which kind of timestamp we have. Type. Whoa, this type definition looks very scary. And if I uncomment it, okay, but we still can comment it out, and we can try to give it this magical is specified. So let's do this. Woo! Data flow generic. This stuff I can also say blah 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 blah, but here I will say U64. Will it be happy now? Looks like it. So now I don't execute advance even. Oh, and if you don't execute, so like you just execute, you call this 10 times, but since we never advanced anything, it always prints 0. So that's how, okay. And then if I uncomment it, then it should work now. Yeah, exactly. And then if I uncomment this, it should also print everything in correct order, ordered by timestamp. Less than. So we can advance this timestamp via the advance2 method, which restricts the timestamp we can use to those greater or equal to whatever timestamp is supplied as the argument. The advance2 method is a big deal. This is the moment in the computation where our program reveals to the system and through the system to all other Dataflow workers that we might soon be able to announce a timestamp as complete. There may still be records in flight bearing that timestamp, but as they are retired, the system can finally report that progress has been made. The probe structure is how we learn about the possibility of timestamp data at some point in the Dataflow graph. We can at any point consult a probe with the less than method and ask whether it is still possible that we might see a time less than the argument at that point in the Dataflow graph. There is also a less equal method if you prefer that. Putting a probe after the inspect operator, which passes through all data it receives as input, only after invoking its method tells us whether we should expect to see the method associated with inspect fire again for a given timestamp. If we are told we won't see any more messages with timestamp t after the inspect, then the inspect won't see any either. The less than and less equal methods are only place where we learn about the state of the rest of the system. Oh, these methods are non-blocking. They always return immediately with either yes, you might see such a timestamp, or and no, you will not see such time. So this is like reports the current timestamp, but this advances the current epoch to next. Okay. So progress information is relatively, I probably should just fix it like that so that we don't need to constantly adjust it. It's relatively passive. We get to observe what happens in the rest of the system and perhaps change our behavior based on the amount of progress. We do not get to tell the system what to do next and just get to see what has happened since last we checked. This passive approach to coordination allows the system to operate with minimal overhead. Okay. Finally, let's talk about how to create timely data flows. So far, I must admit, it doesn't make a whole lot of sense to me. Like, I know that data flow programming in general is about creating those independent workers and setting up connections between them, and then you send data between that, and that's kind of how it should operate. And there is some stuff here that kind of looks like that, like this exchange thing, but all the stuff about timestamps I still don't really get. Let's see if any more examples will make more sense. Let's talk about how to create timely data flows. This section will be a bit of a tough tour through a bit of a tough, yeah. A tour through the data flow construction process, ignoring for the moment details about the interesting ways in which you can get data into and out of your data flow. Okay, so we start again from this like super simple example. Okay. So Timely very much assumes that you are going to build the same data flow on each work. You don't literally have to. In that, you could build a data flow from user input with random number generator, like things like that. Please don't. It will not be a good use of your time. Okay. Source of data. So first we need to input data. Okay, makes sense. Almost all operators in Timely can only be defined from a source of data with a few exceptions. One of those exceptions is the two-stream operator, which is defined for various types and which takes a scope as an argument and produces a stream in that scope. Our input handle type from previous example has a two-stream method, as well as any types that can be turned into an iterator. Okay, so interactive input sounds cool. I guess example doesn't accept arguments. So I guess this like worker thing doesn't really matter then, but this is accepting arguments. Okay, I see. So that is input to stream scope, and this is like, okay. What did we do with streams before? We did inspect on them, right? Can we do inspect on this thing as well? Okay, nothing happens right now. I guess. Let's just do it like that. So that will be our worker ID, and that will be our worker index. And this will be then X, right? This is value. Okay, doesn't like it. Why don't you like it? Of time must be valid. Cannot. Yeah, I need to move in, I guess. How did it print before? Inspect X println sin X. I don't see an issue here. Okay, if I just say this, okay, that works. So that's the issue. How did they do that before? Index. They created. Okay, see. So, yeah, because if I try to do that, then I guess it will move in worker struct itself in the scene. So, worker ID. Let's do that. I really don't like the naming of this index scene because it's so confusing. So let's see if anything will happen now. Okay, something has happened. So they have Okay, let's make it also go to 10 because otherwise it's confusing. So now each of those workers prints 10 numbers. 9. Yeah, exactly. And they execute in parallel, as we can see. Okay, that's good. I wonder if... Okay, that input is empty, so nothing has been printed. String new. Okay, doesn't make much sense. Interactive input with which you cannot interact, but okay. There are other sources of input that are a bit more advanced. One, we learn how to create custom operators. The source method will allow us to create a custom operator with 0 input streams and 1 output stream, which looks like a source of data. Also, the capture and replay traits that allow us to exfiltrate the contents of a stream from one data flow and reload it into another data flow. Okay. Observing outputs. There are a few ways to do that, but the simplest way by far is inspect. Okay, we are kind of going a bit faster because we already have inspect here. The inspect operator is called with a closure, and it ensures that the closure is run on each record that passes through the operator. This closure can do just about anything from printing to the screen or writes into a file. The simple example turns the sequence 0 through 9 into a stream and then prints the result to the screen. Okay, inspecting batches. That we also already saw. Whose closure gets access to whole batches of records at a time, just like the underlying operator. More precisely, inspect batch takes the closure of two parameters. First, the timestamp of a batch, and second, reference to the batch itself. Can be especially helpful. Puts more efficiently. Okay, that we also already saw. Capturing streams. The capture traits provides a mechanism for exfiltrating a stream from a data flow into information that can be replayed in other data flows. The trait is pretty general and can even capture a stream to a binary writer that can be read back from to reconstruct the stream. Okay. Which turns the stream into a shared queue of events, which are the sequence of events that operator is exposed to. Data arriving and notifications of progress through the input stream. The capture method is used in many of Timely documentation texts to extract the stream and verify that it is correct. Okay. Let's try it. I did something really wrong. So input to stream 0 to stream scope. Here data. So that's how we do that. Scope capture to stream scope capture data 2. I really hope it will have some more complete example later on, because so far I'm still very confused about what it does. So we get like now data 1 extract, data 2 extract. Okay. Oh, that also should be okay. Just like really, that's This is slightly annoying. It again doesn't know what my capture event. Forgot what? Okay, let's try it with the other thing. It's slightly annoying that it constantly switches between this timely example and like this stuff because it just adds additional complication. I wish they just always use this form that you would use for your actual program. But whatever, let's run it. I don't understand what is happening there. It's like, okay, we created streams. Then we call this capture thing. Captures the stream using Rust's MPCS channel. So I guess it sends it to a channel. And this thing receives it from sequence. So it's just like it sends data to a channel and this thing just receives data from a channel. Okay, that's nothing happens. Fine. Finally, mapping, map variants, filtering, logical partitioning. Okay, that finally looks like something that is useful. So, in between introducing streams of data and inspecting or capturing the output, we'll probably want to do some computation on those data. Yay! There are a lot of things that you can do, and Timely comes with a set of generally useful operators built in. We will survey a few of these, but this list will be necessarily incomplete. The operators are pretty easy to write and keep showing up. Okay, let's first also look at the docs and see what they include. Oh, so there is a bunch of stuff. Aggregation, branch, broadcast, capture, concat, count, delay, enter, leave, exchange, feedback, filter, flow controlled, generic input, inspect, map, partition, probe, reclock to stream. Okay, sounds pretty cool. So this is just like map. To each record. Okay, so that is like exactly the program we had before, but now it maps number adding 1 to them. Okay, let's do that. Why not? Okay. I always want to run it with several workers so that we see how it behaves when it's distributed. So in this sense, it just duplicates everything, right? I wonder if I just add this. Will it have any effect? Oh yeah, I forgot. So, let's see what happens. You know, so maybe let's make it a bit smaller so that we can see the whole computation there. So, 2424. So it executes it twice, but then because both streams introduce also data, but then it get exchanged between them, and they essentially process it twice then. So okay. The closure map takes own data as input, which means you are able to mutate it as you like without cloning or copying the data. For example, if you have a stream of string data, then you could uppercase the stream contents without having to make a second copy. And with all the benefits that entails. Okay, that's pretty cool. Let's try to do that. Well, actually, well, we can do something like that. Okay, it works. It's pretty neat. There are a few variants of map with different functionality. For example, the map in place meta takes a closure which receives a mutable reference. Flat map method takes input data and allows you to closure transform each element to an iterator which into output stream. Oh, okay, that's pretty cool. Let's maybe, can we do something like that? So I want to be able to say, oh, it doesn't know how to exchange its data. Okay, for now, let's just comment it out. But this is interesting. And then let's do this. Say flat map. And then we say string, I guess. And here we can then say something. To stream flat map. What? Okay, I get it. So flat map is not flattening input. It, of course, if you output a sequence, then it will flatten that. So let's then do just this. So A, B, C, 1, word 2, and then just say return S. Let's just do 2 copies. Okay, it doesn't want to return that. It's not implemented for. Okay, let's do slice. Now it will not like, yeah, cannot. Okay, let's do vector then. Okay, now it's satisfied. And we can now do mapping where we say, let's now do uppercase. Okay, that looks actually like just normal work with collections. We don't exchange any data, so you'll just get from each worker, we get 2 copies of this data because we copy it here. If I remove that map, we should only see 1 copy from each worker. Yes. Okay, that sounds cool. Then we can also filter Okay, that is boring. It's like map. So filter receives reference to the data. Okay. Logical partitioning. There are two operators for splitting and combining streams, partition and concat. The partition operator takes two arguments, a number of results in streams to produce, and a closure which takes each record to a pair of the target partition identifier and the output record. The output of partition is a list of streams, where each stream contains those elements mapped to the stream under the closure. Okay. So this is also like partition method on collections, right? On iterators. Okay. So let's just split it between words and one letter things. And does it know the data of input? Yeah, it knows that it's string. Okay, that's pretty cool. Then input length. You can say if input length is larger than 1, we should return 0. And let's actually map it to second thing. And the output record. And we can also, by the way, change record, but in this case, we just return it. Otherwise, we say 0 input, right? So what is happening then? Oh, and now we cannot call inspect because that will be then streams, right? It's not one stream, it's two. Can I do something like that? Yes, I can. Okay. So yeah, everything got to stream 0. Actually, let's now switch it. Words got to stream 1, right? Let's switch it and see that it really works. Splendid. Now, of course, the cool thing as well, stream 1, stream 0. Can I make one worker process only one stream and another one process only the other stream? Oh, yeah, I can, I guess, say if we can probably do this, right? Why not? So now, okay, that's pretty cool. I split the stream in two parts. Letters went to stream 1, words went to stream 0. And then I made, using this trick with worker ID, I made each worker work only on corresponding stream. That's pretty nice. So partition only logically partitions the data. It does not move the data between workers. Concat takes two streams and produces one output stream containing elements sent alone either. So then move that, and we can make it we of course need to exchange. Don't need for now. God, we do need. Is it moved? Streams. Inspect. I'm returning it accidentally. Okay. I shouldn't return it accidentally. So both streams. Okay, we are moving now. Can we do that and that? Yes. Okay. So now we have still logic where each worker processes its own stream, but then both workers also process both streams. Okay, that's pretty nice. There's also a concatenate method defined for scopes which collect all streams from a supplied vector, effectively undoing the work of partition in one operator. Concat and concatenate are also not doing any kind of shuffle or exchange. To complement the logical partitioning of partition, Timely also provides the physical partitioning operator exchange, which routes records to a worker based on a supplied closure. The exchange operator does not change the content of the stream, but rather the distribution of elements to the workers. This operator can be important if you would like to collect records before printing statistics to the screen, or otherwise do some work that requires a specific data distribution. Operators that require specific data distribution will ensure that this occurs as part of the definition, as the programmer should not need to invoke exchange. There are times where exchange can be useful. For example, if a stream is used by two operators requiring the same distribution, simply using the stream twice will cause duplicate data exchange as each operator satisfies its requirements. So it makes sense to invoke exchange to move the data once, at which point the two operators will no longer require serialization. Okay. There are any number of other operators, most of which you should be able to find in the Timely Dataflow operators module. We already checked it out, so that's this thingy. Scanning through the documentation for this model may lead you to operators that you need, and alternatively, the implementations may say how to construct similar operators. Okay. Creating operators. I actually think I will finish today at that, because I think this is... I know, we have worked example. Okay, let's persevere till working example. Do I want to go through the whole creating operator? So, and working example, what do they do? It's word count. Okay, let's do that. So, how to create custom operators? So, you just need to write a closure that says, giving a handle to my inputs and outputs, what do I do when Timely asks me to run? Let's look at an example. Stream. Guess this thing just does increment on operator. So can I write it here? I still want to try to make stuff work with this more explicit thingy instead of using it inside example. Okay, now it seems that it will compile. So we have this stuff to stream scope that we already saw. Unary creates a new data flow operator that partitions its input streams by a parallelization strategy packed and repeatedly invokes logic. Packed is the first parameter, name constructor. Okay. The function returned by the function passed as constructor. Okay. Here we return closure. Okay. And then this type definition looks epic. It's like, whoa. But then let's try to read it. So D2 is some data. B, this constructor is a function that you can call once. So takes ownership of capability timestamp and operator info and returns L. And L is this closure, which is mutable function. It takes mutable reference to input and output handles. Put G plus static. Okay. And returns nothing apparently. So the heart of the mass is data flow operator unary, which is ready to assemble data flow operator with one input and one output. To show distributed input. So this is like pipeline, I guess. A tasteful name increment, and the logic it should execute whenever Timely gives it a chance to do things. Few ways to request how input data should be distributed. So pipeline says don't move anything. Okay. Increment is just a name. So the heart of the logic lies in the closures that bins input and output. These two are handles respectively to the operator's input, from which it can read records, and the operator's output, to which it can send records. Okay. So that is, yeah. Oh, this type is epic. 1, 2, 3, 4, 5, 6 closing greater than thingies. Input has next, so like iterator. Which may return a pair consisting of capability reference time. Yep. And a batch of data. So while make sure that we have deconstructed. So output has one primary method session. So here it works. Which starts up an output session at the indicated time. This session can be given data in various ways. Elements at a time with give. Time with give. So that is what is happening there. And time is just, we got it from input. Okay. Iterator at the time with give iterator. And vector at the time with give content. Okay. So there is also binary when it takes two inputs and ways to distribute the inputs and requires a closure accepting two inputs and one output. There's also a method source which has no inputs. You can call it on a stream for obvious reason, but you call it with scope. So just like other methods except you supply a closure that just takes the output. Okay. Capabilities. We skip the discussion of the capability argument. So this is capability. Okay. Track whether an operator may or may not receive more records per a certain timestamp. So operators, we hold capabilities for sending data at any timestamp. It doesn't use it in the code. Session time. Okay. So essentially we say that we can send data at any timestamp. So the flip side of this is that the system doesn't make any progress until the operator downgrades or discards the capability. You can construct operators with the ability to send data before they receive any data. This is occasionally important for unary and binary operators, but it is crucially important for operators with no inputs. If you want to create an operator that reads from an external source and sends data, you'll need to keep hold of some capability. That's the number up to some limit, each at distinct time. Source. Stateful operators. There are like a bunch of things here, but I don't see any actual example. Okay, let's first try to run this code as well, because I really wonder what will happen. So for new joiners, we are researching Timely Dataflow, the streaming processing library written in Rust, and we are pretty far off already at chapter 3 of the manual. I guess I will do another stream upcoming week where we will finish up this part of the documentation at least. But for now, let's try to run this example where they construct, whoa, a custom operator, and nothing happens. Shall we do like inspect here? I guess let's do inspect to see what it outputs, right? So as usual. Oh, we cannot inspect. I think I need to operators. I need to do it like that, right? Yes, okay. And let's also make sure that we don't, okay. So we just like did increment. If I do like increment by 2, okay. So this is like scheduling, get some data, downgrade capability. Okay, I will just skip this part for now, honestly, because I don't see how it's relevant to what we're trying to do here, meaning understand anything at all at this point. Stateful operators. Closure, it can capture any state, taking ownership. Larger we have seen so far. Okay. So how far? So this is like stateful increment. Okay, so they capture variables then here, and then if they don't, they only return stuff if it's larger than this maximum. Okay, but that actually it will still do the same thing, right? It doesn't really matter because every time we see something, if you say like 4, or let's do 5, then we should see only numbers that are larger than 5, right? Okay, it works. It's an associated frontier. Must be greater or equal to some element of that list. That's correct. Let's say we can do this data. Okay. Okay, this is also something like super specific to the implementation. I think we can skip it for now. A worked example. Okay, let's see finally an example of word count. How to do word count in this scene. Since text changes as time moves along, some new text are added and some old text are retracted. We don't know why this happens, we just get told about the changes. Our new job is to maintain the word count computation in the face of arbitrary changes to the collection of text as promptly as possible. So they model the text now as list of pairs of times, which will be U64 integers with list of changes, which are each pair string and I64. Gains in the text and whether it has been added or removed. We are going to write a program that is the moral equivalent of the following sequential Rust program. From a sequence of changes to the occurrence of text, produce the change counts of words in that text. Get history, which is a vector of tuples of U64 with vectors of strings with if they were added or removed, so plus ones and minus ones. They create a hash map for each of those times. They do in history drain, they take text and if, they take words from text, then they take counts and they calculate the amount of scene adding or subtracting frequencies. Okay, makes sense. This program is fairly straightforward. Hopefully you understand its intent, even if you aren't familiar with every method and type. However, the program is also very specific about what must happen. We process the history in order, and for each time we process the text changes in order. And we will gain the ability to scale out to multiple workers. Okay. So we can send text which will show us the text backed. Okay. So let's remove useless stuff. Sure. So first we set input and probe. Then we create data flow. We say we take input, we convert it to stream, we print each of those x's, and then insert the progress probe into stream. For each of the rounds, input sends one record into the corresponding timely at the current epoch. Okay. Advance to next round, and then it orders them. It's strictly less than time. Okay. As usual, let's run it with 2 workers. Nothing happens with one worker. It prints it 10 times. Okay, let's make it a bit manageable. Okay. So input handle is how we supply data to the computation. And the probe handle is how we check whether the computation is complete up through certain inputs. I mean, a finished probe is the only way to understand how much progress we've made. Okay. Then we feed some data, so that is data feeding. There's several. First, we send some data into input, which allows the data to circulate through the workers along the data flow. This data will be of type string I64. Second, we advance to tell Timely Dataflow that we have ceased sending data for round and anything before it. Okay. At this point, Timely can start reasoning about round becoming complete once all the associated data makes their way through the data flow. Finally, we repeatedly step the worker until probe reports that it has caught up to round +1, meaning the data for round are fully flushed from the system. Okay. All this time tracking is very confusing so far for me. I don't really get it, but fine. Breaking text into words. And breaks them into many parts with the same I64 value, because if we are adding some text, we add the words, and if subtracting text, we'll subtract the words. Okay. So here we use flat map, okay, where we take the text in div. Of course, we will need to add, no. Oh, doesn't satisfy iterator. Really? Okay, let's see if in the finished code they have. Okay, they don't list it, but it is here in examples word count, because I really wonder why it doesn't want to do it now. They don't need to. It's in map, I guess. Yes, okay, so map was the import that we were missing here. And turn it into an iterator. So it takes text in div, and it takes text, splits it white space, then it executes map, normal map, not timely data flow map, moves every word to create a string. I actually prefer to call it a string, because then it makes a bit more sense. And a div, and then collects it into a vector. So essentially, from the string containing multiple words, it creates a vector of like each word together with the count copied with this div thingy. We do a weird collect thing at the end because try to into text. So I guess we will not see anything here right now, right? Let's do that to at least see that it works. Okay, so that was, and if we remove flat map, we will see that it will before just count like the whole thing as one word, right? Exactly. So that was the difference of having it here. So now we are writing an operator for maintaining a word count. We will need to introduce data exchange where the workers communicate with each other to shuffle the data so that the resulting distribution provides correct results. That sounds like MapReduce. Specifically, we are going to distribute the data so that each individual word goes to the same worker, but the words themselves may be distributed across workers. Having exchanged the data, each worker will need a moment of care when it processes its input. Because the data are coming in from multiple workers, they may no longer be in time order. Some workers may have moved through their input faster than others and may be producing data for the next time while others lag behind. This operator means to produce the word count changes as if processed sequentially. And it will need to delay processing changes that come early. Okay, so there is, a lot of code. So I think that was the correct exchange and honorary frontier. Retain. Okay, where does it take retain from? Let's see. We have this stuff we have. Then we have map operator, inspect probe, channels, packed exchange, hash map. So it seems that we have all the imports, but retain thingy. QS entry time retain. Oh. Okay, let's just try to... This code looks very different. Let's just go through that and see what it does. We start with unary frontier. And we have exchange new, where we take x string i64's reference to our data, and we return the length of that as u64. So we built a new unary data flow operator. By the length of the text, which is a deranged way to do it, but we'll need about 5 more lines to properly write hashing code for the string. Second, we give a descriptive name so that the operator is recognizable in login and diagnostic code, so word count. Okay. Then, third and finally, we specify a closure. The closure has an argument which we ignore in the code. It has to do with writing operators that can send output data before they receive any input data, and we will ignore it now. This closure is actually a closure builder. It is a closure that just returns another closure. So that we already saw. So then it allocates some state, queues, counts, and buffer. Sure. And then it creates, this is like the logic. This is the logic of this operator. So those hash maps are moved into the closure. Okay. We read inputs and update counts inside output. Let's do the input reading first. So this is input reading part. Has a next method, and its option returns a pair of time. So that we already saw. It just reads the input and returns the current time. Then we take time retain. Let's try to find this retain method and see what it needs, because I don't. So that should be capability of T. Dataflow edge. So in this case, our capability, where do we define it? So time is here. It will be capability ref capability, and that will be use size actually if you use land, right? Oh, of course. I need to do this thingy. Maybe I can just I don't know, do it like that. You'll understand it. Okay. So this is the type for this thing. Flow operators. Okay, let's look at the compile error and try to see what it will say to us. So no method found for struct capability ref in the current scope. Oh, it needed two arguments, I guess, right? Capability ref takes, oh, okay, I see. So for whom this thing is implemented. So it is implemented for that. We just, I guess, need to import it. I guess. No. What does it say here? For capability, size. Or maybe I just need to say that this is like your size or whatever. What don't you like? Capability ref. Yay. Okay. We specified the type. Let's make this go away. Let's remove this stuff for now. So, Okay, we made this thing compile. This is already good. Let's try to execute it and see what it will do. Oh, okay, well, at least we see that it does count something already. That's pretty good. So let's get back to reading when it compiles. We take this time next method and optionally returns a pair of time and data representing a time data for a timestamp, where time is U64 or usize in this case, since our inputs is I guess exchange returns this length or something like that, not sure. And then we say our plan is to iterate through all available input. The next method doesn't block. Accepting from the time Dataflow system and moving it into our queue hash map. Ready to go. So we take this time, we make it owned, we insert it into the queues, into our queue, which is capability use size, and data replace. And then we extend the collection with this vector of data. Okay. For time, for queue, iter mute. If input frontier less equal time, if do we push to some buffer. Oh god, this is so insane. Ready to go. Each time and vowels pairs that we've queued up, we then check input frontier, which is what tells us whether we might expect more times or not. Okay, so if we know that we cannot expect more times, we then push stuff into buffer. If the time is complete, we extract the data and get ready to act on it. We don't actually act yet because many times may become available at once. We want to process them in order to. So we drop complete time in allocations and sort ready updates by time. Okay. Processing. Then we process those updates, adding stuff. Oh my god. Okay. Okay, let's try to run it with 2 workers, but then okay. And that was the example. Whoa. Okay. Okay, I guess. So that was interesting, but I must admit a bit underwhelming because we only got it to do hash map count with a lot of code. I will give it another try. I think it is quite interesting stuff. I was really impressed in the beginning where we did those count both in single thread, in multiple threads, and multiple processes. But so far, I don't really understand how the system works. I guess we just need to read a bit more. it's some interesting stuff. It's not like anything else I tried before. One good thing though is that it also has more high-level grades. So even if you don't understand it fully, you can still use it through this differential data flow thing, where you have high-level operators. But next time, we will still try to understand it and see how it goes. Thank you for watching. I will see you in a week. That was Modern RetroTech, and have a nice beginning of the week.